Okay. I think I'll just start then. Because we are already a little bit late, but that's okay. Yeah, cool. Welcome to the second number theory tutorial, and apologies for starting a little bit late. So I think we'll just get straight into it today then. Okay. So what we're gonna be going over through today is four things. There'll be four things that I'll be talking about today. So we'll be going over some introductions to the primes. So this entire session will be very oriented around primes. So we'll introduce ourselves to primes first, and then we'll go on to talk about the fundamental theorem of arithmetic. So yeah, it's quite a unique and cool theorem that we'll be going over through. Yeah, we'll be going over today. And then we'll go over the concept of lowest common multiple and greatest common divisor. So the LCM and the GCD. And if we have time, we'll go over the Euler's totient function, which is really cool. Okay, let's get straight into this then. So introduction of primes. I am sure that you've heard of primes before, so I'll just go over this really quickly. So a prime number, it is a positive integer that has exactly two divisors. So these two divisors will be 1 and itself. Yeah, and you can see the first few prime numbers we have over here, 2, 3, 5, 7, 11. You can go through it and check them, and they will only have exactly two divisors. And yeah, so in a similar fashion, if a number does not have exactly two or has more than two factors, we call them composite numbers. So these are the two most, or yeah, we can split the positive integers into these two categories basically, except one number, and that is the number 1. Um, let's go over to the whiteboards. Okay, let's go over the whiteboard. So let's just write this down. So all positive integers are either prime or, I don't know if you can see that. Cool. Either prime or composite, except the number 1. Okay. And why is that? Because we have defined a prime number to be a number with exactly two factors, right? But number 1, it only has one factor exactly. So yeah, so it is not a prime or a composite number because a composite number needs to have more than two factors, but one only has exactly one. And the number 1 is the only number with this property that is neither prime and is also not composite. Yeah, and prime numbers follow no specific fat patterns. I think that's pretty well known. And then we'll later prove that we can't fit a polynomial, so it only generates primes. So there doesn't exist a polynomial that can basically consistently generate primes. Okay, cool. Properties. Let's go over some properties of the primes. I think the first kind of intuitive thing is that there is exactly one even prime, and that number is 2. Why is that? Well, because if you have any other even number that is larger than 2, it will always be a multiple of 2. And in addition to 1 and itself, it will have more than two factors, so that is not a prime. And there are infinitely many primes, and we'll prove that later as well. And this is just an interesting fact that about the distribution of prime numbers, because we've said it doesn't really follow any specific pattern, but we can still count how many prime numbers there are less than a certain number. So it is given by this bound, which is n log n, n over log n. So that is the bound of how many prime numbers are less than n. And it'll get more accurate when we take n to be really large, So when n approaches positive infinity, this bound will get more accurate. Yeah, and I've added a little YouTube link here. It's a really cool video by 3Blue1Brown. I think I watched it a while ago and it was really cool. It's about primes. Okay, let's do a problem then. I think I will, whoops, let's do a problem. So we want to find all positive integers n such that we have 3n minus 4, 4n minus 5, and 5n minus 3 are all primes. Um, let's take, I think about 2 minutes, I think should be enough. And let's have a go at this problem and then I'll go over the solutions later. Cool. We'll take 2 minutes. Okay. I think that's about enough time. I don't think this problem uses that complicated ideas, right? It's quite an introductory problem. So I'll go over the solution and let's migrate over to the whiteboard. So I've copied the problem down. So we have 3n minus 4, 4 times n minus 5, 5 times n minus 3. And we want all of these numbers to be prime. I think a good thing to try at the start of basically every problem is just play around with the problem. Try to sub in random numbers in and see kind of like what you get, right? So we have that n is a positive integer. So let's try subbing in 1 first then. Okay. If n is equal to 1, we have 3 times 1 minus 4, which is equal to negative 1. So that's kind of bad, right? That kind of like busts the thing because negative 1, it cannot be a prime number. So n is equal to 1 doesn't really work. Okay. Let's try n is equal to 2. So we have 3 times 2 minus 4, which is equal to 2. 4 times 2 minus 5, which is equal to 3. And 5 times 2 minus, whoops, minus 3, which is equal to 7. Okay, so we have the numbers 2, 3, and 7, which are all prime. So n equals 2 is kind of good, right? All right, let's try a few more. N is equal to 3. Well, we see that 3 times 3 minus 4, that is equal to 5. So that's still good, but 3, 3 times 4 minus 5, that is 12 minus 5, which is 7. And 3 times 5 minus 3 will be equal to 12. But 12, we can see that it is not a prime. Right, 12 is not a prime. So 3 kind of doesn't work. Just for the sake of time, I am not going to go any further, but I think it is a good idea to try these small cases at the start of your problems. Okay. Then let's have a look at proving why. n equals to 2 is our only solution. How might we go about doing this? I think that the first thing I will notice is that with this number right over here, so I'll write it in blue, this number 5n minus 3, we see that we have an odd number. We have a 5 times by n, and we are also taking away an odd number, which is quite interesting because if, whoops, if n is odd, then we have that 5 times n is odd, right? Because we have an odd number times an odd number. And by extension, 5 times n minus 3 will be even. Why? Because an odd minus an odd will be an even number. So, yeah, if n is odd, 5 times n minus 3 will be even. And we know that the only even prime is 2. So we know that 5 n minus 3 will be equal to 2. And we can solve that, which implies n is 1. And we have tried the n equals 1 case, which doesn't work, right? So n equals 1 is not a solution. And that also means we have proved that. That also means we have proved that all odd n doesn't really work. Okay. Then let's see if n is even then. If n is even, I think another thing I would see is that the 3n minus 4 term, right? The 3n minus 4 term is pretty interesting because n is even, 3 times n is even, and even minus 4, which is an even number, is still even. So we must have 3n minus 4 is equal to 2 because 2 is the only even prime number. And we can solve that to get n is 2. And we have proved that n is equal to 2. Whoops. Yeah. We have proved that n equals to 2 really is a solution. And that is all the solutions from just this little analysis over here. All right. Ooh, let's go back to the next problem. So I think I will be basically going over the solution to this problem, right? Let's have a look. So P and Q are two consecutive odd primes. They are consecutive odd primes, so they can be 3, 5, 5, 7. The next one will be 7 and 11, right? We want to prove that the number P plus Q has at least 3 prime factors, and they don't have to be distinct, right? So 5 plus 7 is equal to 12, which is 2 times 2 times 3, and it has at least 3 prime factors. Okay, let's prove that then. Go to the whiteboard again. Problem 2. So let's have a look at the prime numbers P and Q. And we want to kind of analyze P plus Q, right? The first thing I will say, and the first thing I'll notice, is that P is an odd number, Q is an odd number. So P plus Q, it must be even, right? P plus Q must be even, and I'll write it like this. I'll write it like 2 divides P plus Q. So we have already found one prime factor of P plus Q. That's kind of given it to us for free. And if we want to prove it has at least 3 prime factors, we just need the number P plus Q over 2 to have 2 prime factors, right? At least 2 prime factors. Because if we can do that, then the whole P plus Q number will have 3 factors at least, 3 prime factors at least. And I think the interesting thing we gotta notice is that P plus Q over 2 will be strictly larger than P. right? Because P and Q are consecutive odd primes. Oh, well, not really, but P and Q, P plus Q over 2, it will be strictly larger than P because, yeah, they're not equal. And in a similar way, it will be strictly less than Q, right? In a similar way, there will be strictly less than Q. So we see that kind of this P plus Q term is basically sandwiched between the two primes P and Q, right? P plus Q over 2 sandwiched between the two primes. And the problem condition is that P and Q are two consecutive odd primes. What does that mean? Well, it means that there is no other prime between these two numbers. It means that there's no other primes between these two numbers, P and Q. Okay. Well then that means if P plus Q over 2 is kind of sandwiched between these two, we know that this one is not a prime number. So P plus Q over 2 is not prime. So we must have P plus Q over 2 is equal to A times B, where A and B are just some positive integers that are bigger than 1, right? Cool. So if it's not prime, and then we can express it as A times B. And well, we already kind of found our two more factors that we wanted to find, right? If A and B are both prime, then that's great. We got two primes. But if A and B are not prime, we can kind of break it up into primes, and yeah, we'll still find at least two prime factors in P plus Q over 2. Uh, so we have proven problem 2, which is quite cool. All right, let's go back. Okay, want to prove that there is no polynomial with integer coefficients, so we have such that P of n is prime for every positive integer n. So basically it's saying uh there cannot be a polynomial so that when whatever number I plug into, whatever positive integers I plug into, it will always spit out a prime number. Yeah, it seems pretty ridiculous, right? Because there's no formula to primes. So let's prove this formally then. Let's basically prove this. Okay. We can basically go back to the whiteboard again. Okay, problem 3. Let's consider the polynomial. Let's just consider P of n, and I'll write it out, right? So I'll write it out. Oops, let's do P of x. That will be equal to the sum of a, so that's some coefficient, and x to the power to some power, right? That is basically kind of our definition of a polynomial. You've got x raised to a power times by a coefficient, and we'll add them together. Okay. I want to prove that this thing will not give you primes, right? We want to prove that whatever number we feed into it, they will always at least have some number that is not prime. So let's assume P of n is equal to a prime, right? So that means we plug n into the polynomial, then that will give us a prime number. And let's consider the polynomial of n plus p. So we are just substituting n plus p into this polynomial that we have. So into this one. Let's just have a look then. So I want to claim this one key claim, and that will basically help us solve the problem. And that will be n to the power to some power, I'll call it to the ith power, will be congruent to n plus p to the ith power under mod p. That just means that n to the I, when we divide it by p, it will be equal to the remainder of n plus p to the I when we divide it by p. How do we go about this? We can kind of basically expand. We can basically expand this bracket. Okay, let's expand this bracket then. So, we see that the term at the very start will just be n to the I, right? And we will have a p to the I term at the very end. And in the middle, if we just consider our binomial expansion kind of formula, so we have, let's see if I can remember this. It will be the sum of I choose some index, let's say I choose j, n to the j times p to the I minus j. That is just our binomial expansion formula, right? And we can also see that, wait, we have a p to the I here, so that is obviously divisible by p. And each of these terms here in the summation, it also kind of has a p to the some power term, right? And this power will always be bigger than 0, so there will always be a factor of p. So under mod p, we can kind of just cancel all of these under mod p. And yeah, that pretty much proves it because we have n to the I left over, and that will be obviously congruent to n to the I under mod p. Okay, so now we've proven this, we can go back, right? We can go back and see that p to the p of n plus p, so it's down here. So if I substitute n plus p into our polynomial, that will be equal to the sum of some coefficient times n plus p to the I. And we know that this thing will be congruent to ai times n to the I, right? And that will be congruent because that we already know. That is our definition, right? We already know. So that will be equal to p of n. And that is equal to p, our small prime p, under mod p. So what does that mean? That means that p of, can people actually see that? Yeah. That means p of n plus p will be congruent to 0 mod p. So in other words, whoops. Yeah, so in other words, p, which represents this polynomial, if I substitute n plus p into it, it will be divisible by p, by the small prime p. Now comes the problem, right? If p of n plus p, so this number right over here, if it is some multiple of p, right? If it's some multiple of our small prime, so if big P of n plus p is equal to kp, where p is our small prime, right? Where p is our prime, and k is bigger than 1, well then we have just proven that this thing here is not really prime. This thing here is not prime. So that's bad. So we must have, must have, this thing is bad. So we must have p of n plus p is equal to p. For it to still be a prime, because if it's any other multiple, it'll break. Right. Cool. We can now just keep doing this process, right? So instead of considering this value of n plus p to the I, we can consider n plus 2p to the I, n plus 3p to the I. And I don't really actually care. I don't actually really care how many p's I put after the n. I can have n plus 1,000p, n plus 10,000p. It doesn't matter. And it will always tell me that n plus this many p will be congruent to 0 mod p. And that will force n plus however many p to be a prime, right? However many p to be a prime. And that's really, really bad because we know that a polynomial only has finitely many roots. So a polynomial only has finitely many roots, but we have an infinite um number of inputs such that this polynomial gives you the same prime p, which is a little dubious, right? And in fact that actually can't happen because of this fact right here. So if you consider the polynomial g of x is equal to p of x minus the small prime p, then we are just saying g of x have infinitely many zeros. It has infinitely many roots, which is a really big contradiction to this statement right over here. So that's really bad. Yeah. So we have basically proved that no polynomial patterns for primes actually exist. Okay. Cool. I think that about wraps up the first section of this lecture. So let's go to the next section, which is fundamental theorem of arithmetic, which is, as the name suggests, it's pretty fundamental. It's pretty important to number theory. Okay. Here is the definition then. So we will have the theorem, which is just that every integer greater than 1 is uniquely expressed as a product of prime factors. So if we have some kind of positive integer n, we can represent it in this form where p1, p2, all the way to pk, there are some primes. And the theorem says that this will always happen, and there will always be exactly one way to express this. I think I'll give everyone about 3 to 4 minutes to just have a look at this. 3 to 4 minutes to just have a look at this theorem and think about how you might prove this theorem. Okay, so how you might prove this theorem. Yeah, you have about 3 to 4 minutes, and I'll go over the solution later. Okay. All right. I think that's about enough time. So I'll just go over the proof of this theorem. So, actually, what I had on my next slide was that you have to prove it in both directions, right? So you have to prove this theorem, to prove that every number has at least one prime factorization, which is basically the existence of a prime factorization. And you have to also prove there are at most one prime factorization, which proves the uniqueness part. So to prove this thing, we actually kind of have to do it twice. One going from this way to this way, and then the other way going from this way to this way. Okay, so let's go to the whiteboard. Fundamental theorem of arithmetic. We have to prove that it has exactly one prime factorization. Let's prove the existence part first. Existence. I don't know if that's how you spell existence, but okay. The existence part of the problem is that every prime number, every number has at least one prime factorization. And how we are going to do that is we will use a technique called strong induction. So strong induction. Yeah. Okay. So let's do our base cases then. So base case, n equals to 2. That is good because 2 itself is a prime. So n is equal to 2 has a prime factorization. Let's do one more. N is equal to 3. That is also good, right? That is also good because n equals to 3. 3 is a prime. It also has a prime factorization. Now comes the induction hypothesis. So our hypothesis, whoops, that's not how you spell hypothesis. Hypothesis for all k less than or equal to n, k has at least one prime factorization. Okay, that is well and good. And so our inductive step will be looking at n plus 1. Step, let's look at n plus 1 and see what happens, right? Let's look at it in a few cases. So if n plus 1 is prime, well then we're just done, right? Because n plus 1 is prime, it has a prime factorization. So happy face, we're done. So now assume n plus 1 not prime. Or then that means n plus 1 will have at least two other factors, right? We'll have at least two other factors that are not one in itself, because that is the definition of a composite number. So we can write n plus 1 is equal to a times b for some a and b. And we also know that a and b are both less than or equal to n, because n plus 1 is pretty big, and a times b, they'll both be less than n. So now we can use our hypothesis, right? We can use our induction. Let me just scroll down. We can now use our induction hypothesis. That is A and B both have a prime factorization. So we are basically done with the induction here, right? We are basically done because if A and B both have a prime factorization, then we have proven that n plus 1 actually has a prime factorization as well, because you can just take the primes of A
张永轩，
and multiply
过来，过来，过来。
the primes of B. Okay, cool. Yeah, A times B, that means n plus 1 will have a prime factorization. So we have proven the existence part. We have proven the existence part of the fundamental theorem of arithmetic. So now let's prove uniqueness. Uniqueness, which states that every positive integer n has at most one prime factorization, right? Has at most one prime factorization. Let's suppose not. So we are using a contradiction here. So let's suppose n is equal to p1, p2, p1 alpha 1, p2 alpha 2, dot, 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 pk alpha k. So that is one prime factorization, right? We have just listed out its prime factors and we have multiplied them. Let's suppose there's another one. There's another different prime factorization called q1 beta 1, q2 beta 2. And we can carry on until q of L beta of L. I'm just making up variable names, but that doesn't really matter. Okay, so suppose P1, P2 all the way to PK and Q1, Q2 all the way to QL, all of these are primes. Okay. We want to find a contradiction, right? So let's have a look at this part. And let's consider P1. We know that P1 must divide into the right-hand side, right? Because we have on the left P1 times something is equal to the left-hand side. So P1 must divide into Q1 beta 1, Q2 beta 2, QL beta L. Okay. It must divide into it. So that means, oops, Q1, Q2. Yeah. That means P1 must divide into one of the Qs. It can't divide into two of the Qs, right? Because the Qs are different primes. So it must divide into one of the Qs and one of the Qs exactly. So P1 must divide. Let's just say it divides into Qi beta I. Well, how many P1s are there? There are alpha 1s, right? There are alpha 1 P1s because we have P1 to the power of F1, of alpha 1. So P1 to the power of F alpha 1 must also divide this Qi to the beta I. So now we are actually done, right? Because we have just shown that if we look at every prime on the left, P1, P2, all the way to PK, we can do that for every prime on the left. And it must divide into some distinct prime on the right, right? Because you can't have, say, P1 divides into Q1 and then P2 also divides into Q1. That is not possible, right? Because Q1 is a prime. So we have actually found a match between the left and the right. So these two are matching. So we have proven that these prime factorizations are actually exactly the same, which is a contradiction, right? Because we have just proven that n has exactly one prime factorization. Cool. So that will be our proof of the fundamental theorem of arithmetic. And I'll go straight on to a really classic example. I think most of you have already heard of this example, and that is the fact that there exist infinitely many primes. I'm sure basically everyone here should have heard of this result. And let's just have a look at the proof again and see where does the fundamental theorem of arithmetic actually comes into play. So the overall big idea of the proof is that we can suppose there's a set P1, P2, dot, 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 PK, of primes, and that is all of our primes here. And we consider the number n is equal to p1, p2, dot, 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 pk multiplied together plus 1. Right? That is our standard way of proving that infinitely many primes. So, and then next, what we did was that we looked at the prime factorizations of n, haven't we? We went like if p1 divides n. Well, we went p1 does not divide n, p2 does not divide n, pk does not divide n. So none of our existing primes actually divide n. But here's the thing, right? Here's when the fundamental theorem of arithmetic comes into play. Because we know n has exactly one prime factorization, then in that prime factorization, there must be some prime that is not in our list. Yeah, so we're done. That is basically the same proof you've always known, but I am just adding the part about the fundamental theorem of arithmetic in, so it is clearer. Okay. Let's move on then. Cool. So we have proven this. We have proven the infinitely many primes. Let's go on to the lowest common multiple and the GCD. So I'm sure you've heard of these terms before as well, right? We have GCD as the largest integer that divides both A and B, and it's also LCM is the smallest integer that is a multiple of A and B. I am sure that these definitions are not foreign to you, right? Here is another definition though. So if we have A and B, and let's list out the prime factors of A and B, right? So P1, P2, ordered to PK. We can define the GCD like this. So it is the what's happened? Okay. Yeah, so we have the definition here. Right. So we've just taken the prime factorizations of A and B, and we are saying that the minimum, we define the GCD to be the minimum of the exponent of each prime factor. And we define the LCM of A and B to be the maximum. We take the maximum exponent of each prime factor. How this thing makes sense actually is that, let's go back to the whiteboard. So we have GCD and LCM. An interesting idea we can use is we can express numbers in terms of sets, right? So I'll talk about if I were to express the numbers as sets. Let's just consider number 12. That will be equal to 2 times 2 times 3. And how I will write it is I'll write 12 as a set of 2, 2, and 3. Well, specifically, it's a multi-set, but yeah. So we'll write 12 as 2, 2, and 3. And we will write, let's do another example of 15. So equal to 3 times 2, 3 times 5, sorry. And we'll write it as 3 and 5 as the set. So how does the GCD definition comes into this, right? How does it affect basically whatever notation we have here? Well, what we need to see is that we want to construct another number. Let's just look at the GCD, right? Such that the GCD, GCD will divide into this number. Exactly. And will also divide into this number. That is the set we're trying to construct. How do we actually have division in this notation, right? Let's see. So if 12 is 2, 2, 3, if we consider a number 2 and 3, right? So that is 6, right? Because 2 times 3 is 6. So this set 2, 3 represents 6. We see that this set 2, 3 is actually exactly a subset of 12, right? And that is how we do division or factoring in basically this notation. So if a number's corresponding set is a subset of another number, we can say that the other number will be a multiple of this one. So basically what I'm saying is that this number D and the set that corresponds to this number D must be a subset of both this one and this one. And we want the greatest subset of this. So that will be 3, right? Because only 3, the set 3 is a subset of both this one and this one. Okay. There's another visual way of saying this, which is basically sets relate really well to Venn diagrams, right? So if we have the set A and B. So that is the big, so let's just have A as a set of a number. We can have A is 2, 2, 3. That is our set. And B will be our set of 3 and 5. Cool. We see that 3 belongs to both sets, right? 3, so 3 goes here. 5 will go here, and the 2 will go here. What we're doing is actually we are just taking the intersection. Whoops. What's happened? Yeah. We are just taking the intersection of these two sets, right? And the 3 lies in the middle of these two sets. So 3 is the greatest common divisor. Okay. Let's move on to the LCM. We can actually do the exact same thing. And that is if we have a set and another set like this. A, B, using the example before, we have 2, 2, and 3 and 5. Oops, you can't see this. Okay. We have 2, 2, 3, and 5. To take the LCM, we actually just need to take the union. So we are taking this entire shaded region. So we are grabbing the 2, the 2, the 3, and the 5. So we're grabbing 2 2s, 1 3, and 1 5. So the LCM will just be 2 times 2 times 3 times 5, which will be 4 times 15, which is 60. So in this case, we just have the LCM of 12 and 15 is equal to 60. So you can kind of go verify it. I think it's correct. So this notation basically kind of introduces the Venn diagram idea into finding the GCD and the LCM. And we have, by the fundamental theorem of arithmetic, each of these is actually unique, right? Which is pretty cool. Okay. That's just a little bit of introduction into thinking numbers as sets. Okay. I think I will round off the class with one final example because I think we are a little tight on time, but that's okay. Let's have one final problem. What's happened? Problem. So let A and B be positive integers. I will claim, or I'll try to get you guys to prove that A times B will be equal to its GCD times its LCM. Whoops. And just a little hint, you can probably do this basically instantly if you think about the set and the Venn diagram from before. So I think I'll be going over the solution very soon. I think I'll take about 2 minutes and then I'll go over the solution. Okay, cool. I think I will go over the solution to this problem now. All right. So we have, well, let's just use what we had before, right? We can have A is equal to a set of some prime numbers. I don't really care what that is for now, because we're trying to prove it for general A anyway, right? And B is equal to some kind of set of its prime numbers. Let's call this set big A and let's call this set big B. And we will draw out the Venn diagram. Okay, so we have two circles. This one represents A, this one represents B. And we know from before that the LCM, sorry, the GCD is this middle part that is shaded in blue. And the LCM will be, I think I'll use red. The LCM is this part, this entire region, right? Shaded by red. Okay. And we also know that if we have the number A times B, what I'm doing is I'm just grabbing all of the elements in the set B, in the big set B, and I'm combining it with the element in big set A, right? Because if you think about it, if I have 12 times 15, that will be 2, 2, 3, and this one will be 3, 5. So the result, which I think is 180, this will just be the set that is, oh my gosh, I'm not showing the thing. Okay. If we have 12 times 15, that will be 223. 15 is 3, 5. That will be 180. And the set will just be 2, 2, 3, 3, 5. All right. We can probably check the prime factorization of 180, but I'm pretty confident that this is the set. And you notice how the 2 to 3 here comes from the 12 and the 3, 5 comes from the 15. So the number A times B is actually just, I'm taking A and I'm also taking B. So in that case, we have counted this part. So we have counted this part, so not including the middle intersection once. We have counted this part, so the symmetrical opposite side once. But we have counted the middle twice, right? So that is actually just one of this, and then two of these, which will represent our set A times B right over here. So that is on the left-hand side. So we have A times B. What about on the right-hand side? The GCD times the LCM. Well, we're kind of done, right? Because we know that these two numbers, when you times together, you're also adding together their sets. So the GCD is actually just the blue set, and the LCM is the big red set. So the LCM will add this part once, and then this part once. And then when we multiply by the GCD, we're adding on the blue section again. So on the right, we are also counting the exact same set, right? Because we've just counted the exact same set in two different ways. On the left, we counted it as this big A circle added to this big B circle. On the right, we kind of counted it as the intersection and then add on the red shaded part. So both ways are actually counting the exact same thing. So they are actually equal. And we are done. Okay, cool. I think that will be all we have time for today. So we'll wrap up the lecture here. Thank you everyone for coming, and you're welcome to leave now. Okay, bye-bye.